first thing I want to start with is not center of mass, but I want to go back and touch on elastic collisions again. And I talked about this in class. I didn't actually show you the equations, but we looked at the PhET simulations, and then we talked about the difference in elastic and inelastic. Please remember the difference. Please remember that with an elastic collision, conservation of kinetic and energy, when you have a perfectly elastic collision, will always be there. You'll always have energy conserved, kinetic energy conserved, and you'll have momentum conserved. So that's very important to remember with elastic collisions, okay? Now, now this is very important. Notice these two equations right here. Now, basically, what is this equation here? Well, they're deriving these equations, okay? They're deriving these equations. So if you want to find the final velocity of A and the final velocity of B, there are your equations, but these equations have a stipulation. This is when B has a 0 initial velocity. That's the only time that you can use them. All right, those two. Here's the final velocity, and actually we should say VA final, okay, and VB final, all right, and of course this is VA initial, okay. So please make sure you write it that way. In other words, if you have a situation, well, let's say we got two bowling balls and they're going to collide, or a bowling ball is going to collide with a beach ball, okay? And so we got a beach ball, and the bowling ball is moving with a velocity of 2 meters per second to the east, and that's the initial velocity. And the initial velocity of the beach ball is 0 meters per second, okay? This is A, this is B, okay? All right? That's the only time you can use those equations. If both are moving, we've got another equation that we'll use that I'm going to send to you. I'm going to derive it for you because I don't want to take 10 minutes of class to do the derivation. I'm going to derive it for you, and I'm going to post it in Blackboard, and I'm going to email it to you, probably today. But if you have elastic collision in which both objects are moving initially, then your equation's going to change a little bit, okay? It's going to actually look like this. It's going to be, and I'll use A since we're using here A. You can use 1 and 2, doesn't matter. So it'll be VA initial plus VA final is equal to VA, yeah, that's right, VB initial plus VB final, okay? And this is for, now that's not all you'll have to do, because what you're going to have is two unknowns. You'll have to set one equal to the other, solve it, and then go back and plug it in. You follow me? So a little bit more algebra involved. And I'm going to derive this and show you how we come to that. It's real easy. You can probably do it without me showing you. And then we will probably work one of these problems next week when we come back, just for kicks, and maybe two, because I could put one on the final. All right. So this is for when A and B have initial velocities. Have I'm going to say this, non-zero initial velocity, okay? All right. Okay. So let me rewrite that. So that is what did I say? VA initial plus VA final is equal to VB initial plus VB final. And see, if what you notice is like terms are on the same side. Okay. All right. Initially, if you look at momentum, it's not like that. So you have to do a little derivation. All right. And that is this equation right here. All right. Then you set one equal to the other, solve it, and then go back and plug it in. Okay? Once you solve for the final velocity, then you can plug it in and find the final velocity of the other. Okay? All right. But please remember, it all elastic, and inelastic too, because inelastic momentum's always conserved, always, all right? It always stems back to this right here. Momentum initial has to equal momentum final, period, all right? The only difference with is that in inelastic you have the total kinetic energy is less than after the collision, okay? In other words, there's a loss of kinetic energy. It's less than it was initially, all right? Okay. Now these problems, since the equations are kind of long, they take up a lot of space on a piece of paper, but still, you just have to make sure you keep your numbers right. And another thing, keep your signs right. If one ball's moving east and the other one's moving west, then you got to give the west one a negative sign. Okay, it's not going to tell you that in the problem. You just got to remember conceptually, oh yeah, it's moving the opposite direction, I got to make it negative, okay? You can have collisions when they're both moving positive or both moving negative. That happens too. One's moving a little faster than the other. And it can be elastic, okay? So that can happen too. They don't always have to be moving opposite directions. They can be one going slow and the other one going fast, and they hit and elastically collide. That can happen too, all right? You can have them at angles, and guess what you get to do when they're at angles? You get to do what? You get to do the components of x and the components of y, and then to find the magnitude and the angle, you take the what? Square root of the squares, and then to find the direction, you do arctan. So it can get a little squirrely. It can get really, you're going to need legal pieces of paper to solve the problem. Well, if I'm writing, you will, because I write big. Right. Some of you write small, and you can do 25 problems on one sheet of paper. I don't know how you do that, but you do, all right? But, because some of you turn it in, and it's like, But it's legible. At least it's legible. All right, I can't always say that. Okay, so just please remember the difference in elastic and inelastic and what is conserved and what is not conserved, okay? But momentum's always conserved. All right, energy is not in inelastic. All right, so center of mass. If you've ever wondered how in the world do they make that saber so well balanced? A good sword maker you'll be able to balance the sword right close to the tang, right close to the hand guard. Okay, I think they call it the tang or the hilt on the sword. And if you've ever watched these, Forged in Fire, you ever watched that? They'll do that. They'll take those swords and they'll hold it up, and if it's real close to the tang or the hilt on the sword, I think it's different I think it's called a hilt on a knife and a tang on a sword. I don't know. I can't remember. But anyway, it'll balance well. If you watch Pirates of the Caribbean, if you remember, Will was a really good sword manufacturer because his would balance real close to the handle. Well, why is that? Well, you don't want all the weight out on the end of the blade. My God, do you realize how hard that is to swing? Can you imagine those guys, those knights that fought with those big old long broadswords? How in the world did they do that with all that armor on? Some of them were as long as one of these tables. They were huge, and the metal was thick on them, but they were well balanced. And they could swing those things. Boy, I'll tell you what, Schwarzenegger could swing one, and so could Mel Gibson. I'd love to know how much practice training they did, but now, buddy, you had to be a man to swing with those. Because, man, you're in combat. You can't, like you were when you was kids, You had to be Master Jedi. I mean, really. You had to be Obi-Wan Kenobi or something, all right? You had to be really good. That's really where that comes. The Jedi come from the philosophy of the knights, and you know what I mean, from the medieval times. So, anyway, I've always wanted to duel. I've always kind of wanted to take some dueling classes. I don't know. I'd probably get my head cut off. But anyway, probably shouldn't. But I said all that to say this. This is how they derive it, okay? Or this is how they determine where or how to make an object where the center of mass is where you want it, like a sword or a knife, okay? I don't know if you've ever, I've picked up knives before, and they're like, you pick them up, it's like, lunk. I'm like, nah, you don't want that because it's too heavy on the end. You want a well-balanced blade, okay? And there's an art to it, okay? But notice it's a simple equation, so notice, and it is, notice it is a vector quantity, okay? Vector quantity, and R, of course, is the position. Please understand my variables here. R is position CM, center of mass. I think you can kind of determine here by inferring, deductive reasoning, what these symbols represent. And so you just take the mass of and the radius of 1 plus the mass radius 2 and so on and so forth, all right? If you want to find the center of mass of several objects that are hooked together or put together, okay, or touching, okay? And that's it. And so they use the sigma there, the sum of the masses, and the radii divided by the sum of all the masses. And by the way, that is total mass. Please understand that is the total mass, okay? All right, that's the sum of all the masses. And so center of mass. And likewise, what about the momentum? What if we have, what I guess you might could call it the center of momentum? Well, in a sense, you could call it that. Notice if you take the total mass, and by the way, that tells you the capital M is total mass. If you take the total mass of all the objects times the center of mass velocity. Well, how do I find the center of mass velocity? Well, you take the mass of 1, the velocity of 1, mass of 2, velocity of 2, and so forth, and divide it by the total mass, and that will give you the center of mass velocity. Okay, the center of mass velocity. Okay, I don't know if you've ever watched objects move, especially an object that's moving that has rotational motion, or even that has linear motion. More so rotational motion. You'll notice that the velocity at the center and the velocity out on the perimeter totally different. Look at a merry-go-round. The velocity towards the center of a merry-go-round is much, much lower than it is out on the edge of the merry-go-round. I mean, that's where it's spinning bar. You know, if you sit close to the center, it's not quite as bad. That's where I sit. I always get close to the center. You know, I can't go around in a circle. I almost throw up just thinking about it, okay? I can't hack it. I can hack roller coasters, but I can't hack going in a circle or up and down real fast. I told y'all about me riding the bullet that time with my old girlfriend. She said, "Come on, let's ride the bullet." And I went, "Oh, God." And I knew it was going to be bad. So I was going to be a man, bless God. I was going to get on there, you know. And, yeah, I got on there all right. And I had to find the commode, too, because all that hamburger come back up. It was not pleasant. Okay. Thankfully, she wasn't around to see that, but anyway. Didn't matter. I didn't marry her. I married somebody else, thankfully. All right, so it worked out. It worked out anyway. All right. Okay? Okay. So center of mass, center of velocity. Notice how the equation is very similar. Okay? You just take the momentums, divide by the total mass. All right? Okay. All right? Okay. Any questions? Ah, dang it. Oh, blah, 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 blah. And I hope you do understand that the answers. Oh, well, let's back up. That's the unit, excuse me. I'm going to make sure you get that. Well, you know what velocity is going to be. Dang it, quit doing that. All right, so what is my radius going to be here? Well, it has to be in what? It can actually be in centimeters, millimeters, whatever you want it to be. As long as you keep the units all the same, it does not have to be in meters. Typically, though, we just like to go ahead and keep it in meters, but it doesn't have to be. All right? So your radius here, you can put centimeters, 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 or meters, 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 whatever you want to put. Kilometers, if we were looking at the center of mass of 2 planets, or a planet and its satellite, or the center of mass of 2 planets. You can do it in kilometers, okay? So again, the unit there would be whatever the unit of length is. But it doesn't have to be meters only. Now, we know acceleration does, we know momentum does, and kilograms, same thing, okay? Same thing. It could be grams here. We could use grams. As long as we use grams on all of them, we can use grams, all right? Because there's not an SI unit, no SI unit for center of mass. Okay? All right? SI unit, though, for momentum is what? Kilograms, meters per second. Okay? All right, any questions? Now, make sure you get that, okay? Discard, stop, don't save, stop.